there's a couple ways that we can add these concurrent forces up. All right? The first, and I probably should tell you this, we can do it graphically, or we can do it using math, trigonometry. Remember the other day we were talking about law of sines and cosines? We can use that. And there's other ways that we can do it, as we'll see here. Okay? I'm not a super big graphical type of person, because when I come into class, in order to do things graphically, I need a scale and I need a protractor. Well, today I don't have a scale or a protractor on me. How many people have a scale on them? One. You have both? So how many people have both a scale and a protractor? Okay, 20% of the people do. But anyway, but you can do this graphically. Everything I'm about ready to talk about, it works graphically. You can get a piece of graph paper, works out real nice, get your protractor, do it. It works out great. Okay? Or you can do it mathematically, and I'll focus or concentrate on that. But the one thing that I want to start out talking about resultants is of concurrent force systems. I want to talk about the triangle law. Okay? This is a very straightforward type law that talks about or will give you the resultant of two vectors. And basically it says if you have two vectors, let's just say a vector like this, and we'll say that's supposed to represent 200 pounds, and a vector like this, and that's supposed to represent 400 pounds. If I have two vectors, okay, all I need to do to find the resultant is I need to take one of the vectors and place it at the tip of the other vector. So what I do is I take this 200-pound vector and I place it at the tip of the 400-pound vector, and then I draw a line or a vector from the beginning of my 400-pound, my first vector, to the tip of the last vector, the 200-pound vector. So you'll hear people, and you'll hear the book refer to this as the tip-to-tail method. It's the triangle law. You got two vectors, place them in a tip-to-tail fashion, and draw a line from the beginning of the first to the end of the last. And that line represents the result. Okay? And graphically, if I had scaled these vectors out, 400 and 200, they don't look like they're too much in scale up here, and I used a protractor to figure out, hey, these are the angles and whatnot, I could then scale my resultant and figure out what it is, and I could actually take my protractor and say, oh, it's acting at such and such angle. Okay? So the triangle law is a good way to come up with a resultant of two vectors. You place the two vectors in a tip-to-tail fashion, and you draw a line from the beginning of the first to the end of the last. You can do that also, this won't look real good, but you can do that in any fashion. I mean, I chose to say 400 plus the 200, right? Well, I could have said, here's the 200, and I'm going to add the 400 to it. Now, that might not look like it because I just sort of sketched it up here on the board, but those resultants would be the same. I mean, if you did that on a piece of paper with a protractor and a scale, you'd see that those resultants would be the same length, and they'd be in the same direction. Okay? So that's called the triangle law. We can do that triangle law graphically, but since, you know, like I said, I don't have a scale or protractor on me today, maybe we should concentrate on doing it mathematically. Okay? Well, how are we going to do this? Let's say my 200-pound vector acts at a 60-degree angle, 60 degrees from horizontal. And let's say my 400-pound vector acts at really a negative 10-degree angle. I'll say, you know, 10 degrees down into the, off horizontal, but into the fourth quadrant, okay? When we're doing angles here, you know this from math class, right? Remember standard position? You got your quadrants, okay? Standard position's taking the angle based off here and going in a counterclockwise fashion. That's a positive angle, and that's sort of what your calculator works on too. You can go the other way, like this, but these are considered negative angles. So a 350-degree angle is the same angle as a negative 10-degree angle, right? Did you know that? Say yes. Do now. Okay. Hey, here's the thing. Somebody got a calculator real quick? This will prove it to you. Okay, got calculator. Give me the cosine of 350 degrees. What is it? 0.98. 0.98, blah, 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 right? Yeah. Give me the cosine of a negative 10 degrees. Same thing, all right? It's the same, you're talking about the same direction, you know? You came out 350 degrees this way or negative 10 degrees that way, all right? So I'm going to call this 10 degrees, but really you know it to be negative 10 degrees if you were punching it into your calculator. So, anyway, how are we going to do this mathematically? Well, what we do is we create the triangle law, tip to tail. So we'd say 400, and then we'd put the 200 on here like this. Okay? So we'll erase this here. And then I draw a resultant. I'll just say R. And that, we call that little triangle an oblique triangle, right? Does that look good? Okay? What's this angle in here? Between the two. Well, this is a line on this 10 degree or negative 10 degree angle, right? So from horizontal, this is 10 degrees. This line is 60 degrees from horizontal. So the distance between, or the angular distance from here to there is 70 degrees. So that would leave this angle being what? 110. Okay? You need to know that interior angle. So here's what you can do. You can do the cosine law. R squared is equal to 400 squared plus 200 squared minus 2 times 400 times 200 cosine of 110. Go ahead and do that for me. Leave it in terms of R squared first. So again, now, as soon as you do this, you find out R squared comes out to be approximately 254,723. You take the square roots both sides, you find out that the resultant R is 504.7. Again, if you're doing this scale-wise and you say, hey, 1 inch equals 100 pounds, you'd find out that this line would be a little over 5 inches long. Okay? Is my answer 504.7? That's part of the, well, pounds, okay. Is that the whole answer? No, it's not the whole answer because this is a vector. That's part of it. That's the magnitude part. We need to know what that angle is, right? Okay? So how are we going to do? So we know R is 504.7, but what's that direction? How are we going to get that? Well, we're going to do it by the sine law. This was an oblique triangle. Let's do the sine law. Okay? You remember the sine law? Okay? The sine law says, hey, take a side, divide it by the sine of the opposite angle, and all the sides and the angles relationships have to be in the same proportion. So 504.7 divided by the sine of 110 is equal to, let's find this angle right here. Okay? Let's call this angle A. So that'd be equal to 200, that's the side over here, divided by the sine of angle A. Okay? And we cross multiply and divide, and we'd come up with the sine of A is equal to 200 sine of 110 degrees divided by 504.7. And you'd find out that the sine of A is what? .37. 0.37 what? You better give me another.
2.
Okay. 0.372. That's not an angle. That's the sine of A. That's a real, that's a proportion, side to side. So what you're going to have to do is take the inverse sine of 0.372 in your calculator, and then you come up with what? 21 point, what did you say, 86? Okay, we'll call it 0.9. Okay? Now, what's that 21.9 degrees off of? Or where is that 21.9 degree angle? It's between the 400-pound vector and the resultant. So, I mean, that's fine to present it that way. Hey, it's 21.9 degrees, but that's between the vectors. It's probably more common to call out something maybe off horizontal or off the x-axis. So really, remember, here's the 400-pound vector. It was 10 degrees off horizontal. Here's this result. It's 21.9 degrees between those two. So really, if you wanted to call it off horizontal, or the x-axis, it'd be at 11.9 degrees. Okay? So watch out. I mean, there's both of these things could be correct. You could say, hey, it's 504.7 pounds at an angle 21.9 degrees off the 400-pound vector. That's probably less typical than saying, oh, it's 504.7 pounds at an angle of 11.9 degrees off horizontal. Okay? Does that make sense? Okay. Just watch, because it's, the angle that we got in here was the angle between those two vectors. That's not, that first vector wasn't on the x-axis. That was someplace else.